Here we are at 5.1. Let me write that down here so I don't forget. 5.1. Polynomial functions and polynomial inequalities. Okay, I got a couple of little definitions here for you. Don't freak out by them too much. When you see examples kind of will bring the definitions to life. Zeros of a polynomial, the number c may be a complex number, is a zero of a polynomial function p of x, and that's how we're going to start kind of referring to polynomials right now. Instead of writing out like this whole long polynomial, we're just going to refer to it as the function p of x. But remember, it can be any polynomial. Okay, so don't get just hung up by it has to be this type of function. We're not learning a new function. If p of c equals 0, this is also expressed by saying that c is a root of a polynomial or a solution of the equation p of x is equal to 0. Literally, that's the mathy way of me saying to you, remember whenever I taught you about quadratics and what do we got to make them equal to? 0. And then whenever you factored them, you'd get like x plus 2, x plus 1. And then when you solved it, you got x equals -2, x equals -1. There you go. That's what all that says right there. Okay. The zeros part though is the getting it equal to 0. So right here, polynomial equations, a polynomial equation in one variable, say the variable x, is an equation that can be written in the form of a sub n xn plus all that other junk. It looks a lot worse than what it is. Okay, where n is a non-negative integer, okay, and a n minus 1, and a out of the 0 are all constants, okay. Assuming that a to the n cannot equal 0, we say such an integer, we say such an equation is of degree n, and a to the n is called the leading coefficient. Once again, that's very mathy, isn't it? Okay, and it's literally saying something that whenever I write this down, you're gonna be like, why didn't they just say that? Because things have to be put in a very vague pattern. I'm gonna say it in a very non-mathematical way. So things have to be put vague so that way I can apply it to everything. Okay. So notice, and I'm gonna make it simple. In your notes, I did it a little bit harder than this. But let's say I made n is equal to 3. Okay. Just for giggles, you don't even have to write this down. I'm just showing you kind of what you're seeing right there. So notice if I have a cubed, then I have x cubed. Then I have plus, well, n minus 1, that's 3 minus 1. A 2 n squared, or sorry, x squared. Plus, well, then I'm just going to have a to the 1, x to the 1, and then anything to the 0 power is a what? 1. Remember that. Everything goes to the 0 power is a 1. So here you just have an a, and that's all equal to 0. But you're probably like, dude, that doesn't help out anything. Well, let's change it up a little bit. How about it look like this? There you go. That's literally all it says. And notice it's saying these guys right here, those are your coefficients, right? These right here, oh, I'm sorry, that's a 3. So notice what this is saying. This right here, this degree, is saying, hey, that's how come we put those in descending order. You've learned that. When you list these out, you put them in descending order. So the degree of the polynomial is a 3. Why do we care about that? Because guess what? What's going to make your life a lot easier? Knowing that this is a polynomial with a degree of 3 says my base function should be a what? X to the power what? 3. It doesn't matter about all the junk past that. You're going to have a lot of stuff doing some stuff in and around it, but the base function of this guy is on the very ends of it are going to look like a cube root. No, sorry, not cube root, a cubic. Okay? So you could say that this guy right here is going to, I know it's a positive. It's a cube, so I know it's going to do this. It's going to come up do some jump, and come back up again. That kind of help you out a little bit, understand what they're saying right now, a little bit, okay? Don't get lost in the math right now, okay? Keep an eye on that leading coefficient, okay? First off, look at it, know if it's negative or positive. Look at the leading power, okay? That's the degree of the polynomial. Look at that and go, okay, that's what my graph is doing. If I drew it out as a base, if I drew this out just as P of X is equal to X cubed, what does it do? You can do that, promise you. The rest of this chapter is going to be pretty easy. Because you can get lost in the math real quick. When I get lost in the math, I go, what is the graph doing that I know the graph is doing? And man, it all clears up. It's like the fog is lifted. Okay? Let's continue on. Look at these right here. Now, this is a verification. Easy verification. You've done these since you were in Dev 2. Verify that the given values of X solve the corresponding polynomial equations. All you're doing here is taking this, and for A, we're taking that 4, and we're going to do what? Plugging where? Everywhere there's an X, right? Okay, so let's do it. Take it and plug in. Come over here, I've got 6, 4 squared minus 6, sorry, that's a 4. Times 4 cubed equals 12 plus 5 times 4. Notice when you do the math of this, I'm just going to kind of help you out there. 4 squared is 16. Right here, you should get 32 on that side. When you do the other side, notice 5 times 4 is 20. 20 plus 12 is 2. That works out. Pretty good on that one. Okay. Now look at the next one though. The next one says, hey, I'm going to give you a new one. How about I give you X is equal to 1 plus 2i? It's still easy enough, but you need to remember something when you're dealing with i's. What's something very important that you remember about when you're dealing with an imaginary number? Gotta stretch your brain. You're gonna be using it a lot more now. Put it right here. What's I squared?
-1.
-1. So when you get I squared, you're actually getting a -1. Okay, so you're gonna have to remember that. So if the math doesn't start working, like what happened? That I squared turned into a -1. Okay. So notice on this one, we can do the same thing. We can plug this whole thing in. It's saying plug this in, and we're gonna do it everywhere there's an X. So I've got 1 plus 2i squared is equal to 2 times 1 plus 2i minus 5. Come over here, that turns into 1 plus 2i. 1 plus 2i. There is a formula for that one if you ever want to know it, but kind of keep it as the FOIL method right now. Here I'm going to distribute, and so I'm going to get what? 2 plus 4i minus 5. On the left-hand side, we're going to FOIL, right? So 1 times 1 is 1. And then I'm going to get a 2i. And then I'm going to get another plus 2i. But then notice I've got a 2 times 2, which is a positive 4. But then that I times I creates a what? A -1. So I'm actually going to have a what there? -4. Okay? So instead of having a positive 4, I'll have a -4 there. You good with that? Okay. Clean up this side. 2 minus 5 is going to give me -3 plus 4i. Then we got to clean up the other side. 1 minus 4 is going to give me a -3 plus 4i is equal to -3 plus. So does that work out? Good with that? I mean, that's kind of like pretty straightforward. Biggest thing on this one, especially moving forward, we're going to be dealing with almost in every single lesson we do in chapter 5. We're going to be dealing with complex numbers. They're going to pop up all the time now. Okay. The only thing you really got to worry about is that I squared. Okay. That thing pops up, you know, if you're multiplying, if you get I squared, it turns into a -1, and it changes the sign from front. Positive go to negative, negatives go to positive. We good on that? You okay with chapter 5 so far? Okay, like I said, this 5-1. Taking our time. I want you to absorb everything. If you have questions, ask. This is usually when people start to say, okay, yeah, this is a college algebra class now. Because if you think about it, up to chapter 4, I mean, except for the graphs, still things have been kind of normal. Okay. But now things are starting to look like math. Okay. Remember, we had this up here, zeros of a polynomial. Zeros, just make it equal to 0. Okay, whenever if I showed you this back in your meeting, everywhere that line crosses the x-axis, that's where you created a 0. Okay, because where is y 0? Everywhere it crosses. You're looking for your x-intercepts. You can think of zeros of a polynomial like x-intercepts. And then remember, we are describing all the polynomials moving forward. We're going to use that definition. So I don't have to write out all of that every single time. We're just going to say, hey, P of X is a polynomial. We're just going to say this broad definition of a polynomial right now. Okay. And all that says there, the degree is always the largest power, which you should be writing things in descending order. Okay. And this right here is your leading coefficient. Think of your transitions. Why do you need to know that? Because if the leading coefficient is negative, your function is flipped. Right? Okay, and also that leading degree, or that degree of the polynomial, tells you what the graph is. That's why I drew this over here. Because that is the graph of x cubed, a base graph. Know your base graph. And I promise you that's going to help you move forward. Like I said, I want to reiterate that. Because even while doing your notes, sometimes I get lost in the math. Because man, it just become a lot. And then I go, hold on. What's the base graph say? And then I can almost picture it in my head on what's supposed to happen. I don't even need to do the math. Okay, I can actually just draw a sketch and be like, there it is. And I'd count that. Okay. Desmos is going to become your friend. Have anybody been using Desmos yet at all? Good. If you're using it, great. I don't mind now. The problem with Desmos, what do you think it is? When can you not use it? On your final. Exactly. So don't get so used to it that it becomes a crutch. Okay. Let it become a helper, not a crutch. Okay. So I want to reiterate that. I don't mind you using tools. Okay. Anybody using the AI at all yet? I ask every semester. Is it just kind of worthless? Is the Hawks AI kind of stupid? I don't know. It is, to me, it's annoying when I run your homework, how I'm on it for like 10 seconds and it pops up already going, hey, you're feeling lost. I'm like, well, I wasn't until you started talking to me. Does it do that to y'all too, or just starts popping up trying to talk to you? Okay. I have no control over that, but I'm not even against you using AI to help you out a little bit. Now to cheat, you can cheat all you want. I'll get you on the final. But it will help explain some stuff, especially these definitions. If you really want to understand a definition, go on to like ChatGPT and literally, I've had to do it on some of these definitions. I'm like, man, y'all work, that's stupid. Because these definitions are not universal. Okay. Other math books say them a lot better. Okay. This one, I don't like the definitions a lot in this textbook. Okay. And I go, man, they made that wordy. So continue on. Behaviors. okay? You're gonna need to know this. Look at the behavior here. I want you to notice a term here. Okay, I don't know if you've heard this before. You will more and more see that little arrow there. Okay, now you've seen me use that arrow, and mathematically it's wrong of me to do that. But it's literally, if I'm writing things, it's me saying, hey, here's where I'm working, and now I'm going over here. That does not mean that when you see it in a math term. Okay, that means approaches. Okay, it's like you're walking. Okay, so that right there, that term says as x approaches infinity or negative infinity. It's saying that's the direction x is going right now. Okay. When we get into calculus, you'll hear things like as x approaches zero, which is how come in calculus we can divide by zero. You still can't really. It's kind of a misnomer because we're saying as x approaches zero, which means I want to see what this thing does when this x gets so infinitely close to zero, it might as well be what? Zero. It might as well be zero. It's still not. But man, we are so infinitely close that nothing's going to change. So that's kind of what's happening. This is your first step into that. Okay. And all this is saying, hey, look at the graph. Look at this guy right here. As x approaches infinity, we know infinity is right here, isn't it? As x gets larger and larger, well, where's it going? It's going to infinity, isn't it? As x approaches infinity here on this side, where's that arrow going? It's approaching infinity. Notice what happens over here on the other side. As x approaches negative infinity, where is it going? It is also approaching where? Infinity. Not negative infinity, it's approaching infinity. Well, what do we know that by? When n is even and the a, the coefficient, the leading coefficient of your polynomial is positive and the power is even, then I know as x approaches infinity, it's going to infinity. As x approaches negative infinity, it's going to infinity. Think of x squared. Well, that right here, that's got kind of a wide base. We could call that probably x to the power of 6. Notice my leading coefficient is a 1. It is positive. This guy is even. And look at look at what's happening to it. On the flip side, if n is odd, well, can anybody tell me what this function kind of looks like right here?
X cubed.
Very good. X cubed. This is an x cubed. Is my coefficient, my leading coefficient here, is it positive or negative? What's in front of that x? What is always in front of an x? 1. Is it positive or negative?
Positive.
Positive. You don't see a negative symbol there, so it is positive. Since it's positive, this is how that function looks. It's base function. Remember what I told you? If you learn the base functions, how much easier this is? So look, I'm going this way. So as x approaches infinity, where's the arrow going? To positive infinity or negative infinity? Where's he going?
Positive.
Positive. The picture tells you. It tells you here. As x approaches negative infinity, though, where's it going? Negative infinity. Y'all kind of get that? I mean, does it make sense? I mean, should you play with it a little bit? But if I literally showed you something like this, forget everything else. You just know the base graph. Show you one that looks like this. First off, and let's do it the other way. Sorry. What's that one look like, though? What did you say?
Negative.
Negative. Negative what? What's the function? It's a negative. You got the negative part. Negative what? What's the function? What does it almost look like?
16.
The cube, right? We just did what? Remember, we flipped it. So it's a negative. Without even looking at anything else on here, just look at this. If you're going this direction, the x, we know we're going negative infinity, right? If we're going this direction, we know we're going positive. Well, where, let's use the green here, as it's going this direction, where's it going? Yeah, negative infinity. Here, the negative infinity is going to positive. So notice just by me doing a sketch, I can say, oh, okay, this is what's happening. As this guy goes this direction, because you got to go to the x value first, right? What's going to happen to that y value? It's going to get larger and larger and larger and larger, right? If I get an x over here, that's going to be a really large y value to get back up to that function. Think of numbers. You're probably getting lost because of infinities. People get confused because it's infinity. How do you calculate infinity? You don't. That's why we're approaching it. You can't calculate it, we just approach it. But what's happening? What is this function doing as it approaches infinity? The y is getting larger. As x gets larger, what happens to the y? It gets larger. As x gets smaller, what happens to the y? Well, as x gets smaller, y gets larger. If that helps you say it that way. Okay. This whole thing here you can print out, but notice it just kind of tells you, look, if a is negative, you're just flipping it. There's the one we just did there. Okay. Good so far? Learning behaviors. Now, I showed you that really ugly polynomial here at the beginning. The base polynomial, p of x, would look something like this, okay? But let's be honest. I said it looked like that. But if I zoomed really far out, right? Like, this is pretty close. This would be like if I zoomed in really, really close, right? But if I zoomed out, like if you're on Desmos and you just took your mouse and just kept scrolling back, we could say that all of this is gone. It's still there. But couldn't you agree that our function would look something like that? I mean, and we're talking, I zoomed way out. We zoomed way out. Okay, we're getting a bird's eye view. You're almost looking from the moon. Okay, you're not going to see all the stuff that's happening around the origin. Okay, so this is what this guy looks here. This is what's happening right here. Graph of a factored polynomial function. Notice we've got x to the fourth. But look at what's happening right near the origin. Now, right here, you can kind of see it. Here's my base graph. Right here. One of these, by the way, the reason for the color change, don't get confused by that. One was done on Desmos and one was done actually from your book. One I pulled in from Desmos. Okay. Notice though, this is the base function, the red, which is a x to the fourth. That's what it would look like with nothing happening to it. It's just x to the power of 4. That's it. We're going to graph it. There we go. Same thing for the blue over here. There's our base one. This other one here is with all that other junk added to it. But can you still see the essence, the direction that you just learned of that x to the power of 4 in this? X to the power of 4 has a positive leading coefficient, which means I'm going to get something doing this. It's a power of 4. It's going to do this. Is there some junk happening in between this part to this part? Yeah, look, we get a dip. We get a hump, we get a dip, and then it comes back up again. But its attitude as it shoots off toward infinity is the same. As x approaches infinity, it's going to infinity. As x approaches negative infinity, it's still going to infinity. It has to. It's going to have that attitude no matter what. It's the stuff that happens in between that we don't know exactly. Does that kind of help you out a little bit? So knowing once, like I said, knowing your base graph again, 3.4, I said it in 3.4. Knowing 3.4 is going to be half the battle of this class. Learn your functions. Okay, x to the power 4, we know it's a parabola, just with a little bit of thicker bottom. 6, a little bit wider. 8, a little wider. And no matter what, it's always going to do this. It's just now we're throwing in some stuff in between. Okay? Any questions? You with me so far? It's all explanation right now. So look at this guy right here. Sketch the graph of the following polynomial function. First off, you know some things. Okay? Is this a positive or negative? We know it's going to go up then, right? Because it's emblematic of what? A power of 2, which is a parabola, right? It's also got a transition. Or sorry, translation. It's going to go where? The whole function is going to be done what?
Down.
Go down by how many? There you go. There's a point. You already have one. You have one right here. Now, before we graph anything, because we're kind of doing this as a review, as x approaches, I want you to set that, no, don't say goes to, approaches negative infinity, what's going to happen? Basically, what's happening to the y? Picture in your head a parabola. Do a sketch. I'm serious right now. If you start learning to do sketches right now, there you go. Yeah, exactly. As it approaches negative infinity, this thing, the p of x, the whole function, okay, is going to go to infinity. Well, how about as x approaches positive infinity? Where's p of x going to go? Exactly. There you go. So you have an idea of where this guy's going now, and now you can graph it. You can come here and go, okay, well, I need to graph this. This is actually just a difference of squares. Okay, x to the 4th minus 1. Remember, you're just finding zeros. Here's the part of finding zeros. You're finding where does the x-intercept happen? Okay, well, let's look at this. X to the 4th minus 1, all equal to 0, because we're finding zeros, finding roots. Difference of squares, remember that's a squared minus b squared is equal to 0. That's going to be x squared plus 1, x squared minus 1. I'm going to kind of just skip to the answers here. Notice when you do this one, now be real careful. You get some answers. How many answers should you get? Let's see if you can remember that. How many answers should you get?
4.
4. There's a problem with that though, isn't there? Watch what's going to happen. Not all of them will be graphable because look what's going to happen right here. Look at this x squared minus 1 all equal to 0. That one's going to be fine, isn't it? Because it's just going to turn x squared is equal to 1. Square root. Hey, what do I got to do with that square root on the right hand side? Plus or minus. So I get x is equal to plus or minus 1. Hey, that just means there's a point here and a point here, right? What about the other one though? There's a problem with that. X squared plus 1 all equal to 0. X squared is equal to negative 1. Square root, plus or minus. So x is equal to what? Plus or minus what?
I.
Or just I. So this one right here has only 2 real solutions, okay? Which means those are the only ones you can graph. You can't graph imaginary numbers on a real plane, okay? So is it still graphable? Yes. That can help you out with that a little bit. And now you have a parabola, of course. There you go. Draw it as good as you can. Do better than me. Hard to draw on a computer screen. Like I said, while a relevant solution, it is not graphable at that point. So the only thing here would be the thing that you can graph are the only two real solutions that you have. Don't overthink it. Okay? You get so far. Nobody lost? Okay. I don't want to lose you. Here's the nice thing. I'm going to show you some little tricks. Get this right here. Sketch the graph of the following polynomial function, paying particular attention to the x-intercepts and the y-intercept, and the behavior as x approaches positive or negative infinity. Okay. First off, let me show you a little thing here that you can start doing. It's going to be helpful on your homework. Can we all agree that there needs to be a leading coefficient? And if you can tell me the leading coefficient, you can tell me whether it's negative, and you can tell me the power, you can tell me a lot about what this graph looks like, can't you? Okay, before anything, you can do that without foiling. Okay, so let me show you how. Look through here. Notice I've got an x here, a negative x. I've got a 2x, and I've got an x. Okay, very simple, right? I'm going to come off to the side here. 1. I'm going to multiply negative x times 2x times x. Simple enough, right? I mean, negative x times 2x is just going to give me what? Negative 2x what? Squared. Times that to another x, what am I going to get? Negative 2x what? Cubed. There's your leading coefficient. And there's the degree of the polynomial. So is my polynomial going up or down? Down. It's going to be flipped, right? What type of function is it? X cubed. I know what x cubed looks like, but I also know it's not just a normal x cubed. It is now a flipped x cubed. So that kind of gives me an idea of what this looks like. And what's even nicer, they've already factored this for me, didn't they? I mean, let's just be honest. Look at this. I've got f of x, okay, is equal to negative x, 2x plus 1, and then x minus 2. I also know this. This is negative. This is odd. Okay, so as x approaches negative infinity, my f of x should be what?
Infinity? Wait, negative. Negative.
Want to go up? Look, let's. Now I'm going to show you. Do this. Watch. You're overthinking again. How hard is it to do this? Draw yourself a picture. Right? Does it have to be perfect right now? No. We know that the base graph, and I'm going to do it just in green so you can see what I'm talking about here. The base graph of x cubed would look like that, right? But ours doesn't look like that, does it? Ours is what? Flipped. So it will look, let's do it in red. Ours is going to look like this. This is going to go this way and go that. So look, now that you have a little quick sketch, we know this is positive infinity. We know this is negative infinity. So as x goes to negative infinity, where is it going? Infinity, exactly. As x approaches positive infinity, where is f of x going? How much did that picture help you? Why aren't you drawing pictures? Draw yourself a quick sketch. And do what I did. Take yourself like some little map colors and go, I know what the base looks like. I know what x cubed looks like. I know what x to the power 3 looks like. There it is. That's what I did in green. I know the leading coefficient is negative, so I got to take this whole guy and flip him on his head, flip him across the x-axis, because that's what happens when you put the negative out front. Now you got something you can graph. Watch what's going to happen here. Hey, aren't you solving again? That's how come we make these things equal to what? 0. Come in here. negative x is equal to 0. 2x plus 1 is equal to 0. X minus 2 is equal to 0. Well, doesn't this just go to x is equal to 0? That's easy enough math right there, right? This right here, subtract 1, 2x is equal to negative 1, divide off the 2, x is equal to negative 1/2. Here, add 2 to both sides, and I get x is equal to 2. And so notice I found 0, negative 1/2, and 2. I can come in here and go, okay, here's why this matters. I know it passes here at 0. I also know it passes at negative 1/2. And I also know it passes at 2. But since you know the graph, now, did I tell you to be exacting on this graph? I just say, give me a rough estimation. Hawks will do the perfect graphing for you, okay? Where it finds vertexes and stuff like that. All I'm saying is, what is this saying? What should this thing look like? Well, we said as x approaches negative infinity, where should my line go? Right here. Where should it go? As x is going this direction, where is y? Up. As x approaches over here at the 2, where's it going? Down. So that means it's got to come up here, down, up, and then back down. Oh, sorry. Lose here the negative 1/2 and my line here comes down, up, and down. So, right? Goes through it. It makes a turn, comes back up and goes through 0, makes a turn somewhere in there, comes back down again. And this right here is where you created the zeros at. Okay. Any questions? We okay on that one? Okay. Well, that's nice. Whenever you're having a graph, okay, that's nice to do. Okay. Let me show you how to do it if you just see a graph. Like they give you a graph in Hawks and they say, hey, turn this into a polynomial. Okay. Look at this guy right here. Let me kind of back up a little bit here. Find the polynomial of lowest possible degree that corresponds to this graph. Okay. There's some steps. Step 1, locate your zeros. And zeros are always where the function does what? Crosses the what? X-axis. Everywhere it crosses that x-axis, that's a 0 for you, okay? So we're going to locate the zeros first. Okay, so step 1, locate zeros. So x is going to equal 0 where? At negative 2, 1, and 2. We all good with that? Can we all realize something? If you don't mind. Let's think about this. To have x equal negative 2, you know, if you go back in time, when I first started teaching about quadratics and stuff like that, there were some of those that we just gave you. And I said, hey, let's take them in what they look like back in time. Well, if I had to reverse this a little bit, couldn't I rewrite every single one of these like this? X plus 2, x minus 1, x minus 2. I mean, that's doable, right? Because if I make those equal to 0 and I solve, that's how I get my negative 2, my 1, and my 2, right? Okay. You get so far? Did you get to there okay? Don't want to lose anybody. Well, look at this. I want you to notice something. We're dealing with p of x. So when I start using p, just remember we're saying p of x is a polynomial, right? When p is 0, that means when p is equal to 0, that means that 0 is what value? My x value, right? When x is 0, what's my y value? Yeah, it says right here, look at the graph. When x is 0, y is -2. So watch this. P is 0, we know that's -2. So let's plug in what we know. When P is equal to 0, okay? I want you to realize we have a form. We still need a leading coefficient, okay? And it's kind of hard to figure out because all we got is x's right now. You can't just multiply all those x's together and get it, okay? Let me show you how you get it. Plug in what we know. We know when x is 0, so we can plug in 0 to everything. So watch what we're going to do here. I have a, don't forget your a, I'm giving you kind of a formula here. I've got x plus 2, x minus 1, x minus 2. All is equal to -2. Well, it's only going to be -2 when x is what? 0. Let's plug in 0. So let's come here, a, 0 plus 2. 0 minus 1. 0 minus 2 is all equal to -2. We can do the math of that. 2 times -1 times -2. Okay, that's going to give us a 4. Okay, you can work that out in a calculator, right? Okay, so notice that actually gives us 4a is equal to -2. Can I solve for a now? Divide off the 4, and I get a is equal to -1/2. And there is your leading coefficient for this whole thing. So when you want to put this all back together, now mind you, right now, they're fine with you keeping it like this with the parentheses. So this would actually equal P of x is equal to -1/2 x plus 2, x minus 1, x minus 2. I don't want to lose you. First off, are you good with locating the zeros? That's easy enough, right? We can all do that. Okay. You're also good with putting them back in the parentheses, right? Do you understand why P of x is equal to -2? Right, because P of 0 is -2. Thinking about the graph, right? Where is x 0? It's equal to 0 here. We come down, there's my -2. All you're doing was what I just did here, where I said, hey, this P of x here, whenever I make it 0, all my x is 0, that's what a function does, okay? It's got to equal this -2, but I've still got this leading coefficient. Well, remember your formula. A to the n, x to the n, we're just trying to figure out what that leading a is. That's why we put that a out front. And we solve for it. Sometimes it's going to go up to 1. And you're going to get x cubed, yada, yada, yada. But if you don't, you just solve for a, and there's your leading guy every single time. Okay? You're moved. Any questions over that? Please email. Don't walk out of class going, man, I am lost completely. Email me. Okay? Try it out in Hawks. But also, guys, use Desmos. Don't use Desmos cheap. Try it out and then start looking at it. Okay? Go, man, does my graph look like this? What does this thing look like? Because you can actually put this in right here into Desmos in that form. You're going to need to make it y equals or a function equals something, but still, you can put that in there and you're going to get this graph out of it. Now, it's not going to foil everything for you, okay? We'll do that moving on into the next chapters. Good? Okay, so that's zeros. I want you to remember that. We've been finding zeros, right? Now, this is a nice way to find zeros because they've been giving them to us, okay? They've already factored it for us, okay? Moving on to the last part of this unit, we're gonna still kind of worry about zeros. Now here, please don't let me start losing you now. We're gonna start dealing with inequalities, okay? Solving polynomial inequalities, okay? The polynomial inequality is any inequality that can be written of the form P of X is less than 0, P of X is less than or equal to 0, P of X is greater than 0, or P of X is greater than or equal to 0. Where P of X, remember, P of X is just some polynomial, okay? We're still getting it, and I'm gonna say this with quotations, you can't see it on the film, equal to 0, okay? Because we're dealing with polynomials, right? We gotta get everything to one side, okay? Still do that. Now I'm going to use some terminology real fast. I have it in your notes, but I'm gonna give it to you right now because unfortunately, not unfortunately, Hawks is just gonna say it like you should just know, okay? And I'm not saying, and you shouldn't, because this is the first time this is the first time you ever heard this word used in a mathematical sense. We are going to use the word strict and not strict. Not like how your parents are strict or not strict. It's a definition. Okay. Strict is this. Any polynomial that does not, hear me, does not. I know your brain wants to kind of flip it around. Strict does not have the or equal to. Okay? So you're going to be dealing with parentheses. Okay? Not strict is these guys right here. Okay? So here we have strict. Here we have not strict. Not strict has that. This has that, which means here you're going to be dealing with parentheses. Here you're going to be dealing with brackets, unless you're going off to infinities, which you always deal with what when you're going up to infinities? Parentheses, always. Why?
Because they're not the value.
You can't ever equal infinity. Think about that way. Because think of the largest number and then add 1. Okay. You can't ever equal infinity. So while something may be not strict on the inside of something, if it shoots off to infinity anywhere, the outsides are always going to be the parentheses. Kind of help you out a little bit? Okay. Really, the strict and not strict is going to be dealing with what's happening with the function on the little part where you're creating the zeros. Okay? And this is what I talked about. If you know your base, hear me out, know your base function, I'm about to save you a lot of time. Doesn't mean you should know how to do the math. Okay? Because it is important. But I'm going to save you some time. So watch. Let me show you what this means first. And then I'll show you how knowing the base graph is going to help. Look at this carefully and read the question. You do need to be very careful reading this, okay? Because do realize they just gave you the same function twice. But they're asking 2 different questions, aren't they? One of them, they're saying all of that junk is less than 0, and it's saying where is it less than 0? The other one is saying where is it greater than or equal to 0? What values make this function greater than 0 when we solve? What values make this function less than 0 when we solve? Think about it. This is almost the same thing you did whenever y'all did linear inequalities, right? Hey, this thing is negative over here or less than this number. Okay, but now we're dealing with polynomials that do this. That's all you're doing. You're figuring out where does this equal this and it's greater than that or less than this. You can change that around. I mean, it doesn't have to be 0. 0 is easier. And that's how we're going to deal with this left 0. So look at it carefully. If you have a graph, to stare at. Makes life easy, right? We know x is equal to 0 where? Am I right? Okay. So look carefully. This is how I'm going to do A. A says, where is x less than 0? That is strict because I know that because it's no equal sign underneath it, right? Okay. Less than 0, doesn't that mean all of that down here below? So we could kind of shadow this in here. Isn't that everything less than 0? Okay. Well, let's think about this for a second. We've got to write this in interval notation. Okay. So we're looking at this as a function of, we're just going to say f of x. Where is f of x less than 0? Well, let's draw ourselves a little picture. Can we say this? First off, we know the zeros, right? This point here, and this point here. This is going to be what? -3, -1, and 2. We could have found that just by solving for all of those, right? That's where I found my zeros. Okay, what's happening at -3? Where's that line going? Think of a domain. Where's it coming from? It's going to come from -infinity, isn't it? So let's look at it. -infinity from here, from -infinity up to -3, I'm going to use a parenthesis because why? It's strict. I can't put a bracket. Hey, where else is it negative? Where else do you see it start to dip? If we're going from left to right, always left to right. Where would it start to go down? Yeah. How about right here at -1, put a parenthesis, and where would it finally cross back up again before going to positive? Huh? The 2? Yeah. Right? Everywhere from -3 back is going to be less than 0. Everything from -1 to 2 is less than 0. There's your answer. So you would put it down like this. -infinity to 3, sorry, to -3. Union -1 to 2. Why don't you try to do B on your own? Get that? Don't forget how you write it though. -3 to -1. Strict on both ends of that. Why? Because nothing shot off where? Yeah, nothing shot off to infinity there. So that's why I'm gonna use brackets on both of them. Then I gotta union that with the 2, but then that one does shoot off to infinity, so it doesn't matter whether it's strict or not strict. You can never equal infinity. And you always do these from left to right. It's just like domain. You found the domain. The domain of this function, when, or the x values you're allowed when x is greater than or equal to 0, are anything between here and here on. Good? Real pretty whenever you have a graph, isn't it? What if you don't have one? This tip brings us into another definition. Continuity. I have two graphs here. Continuous function and a discontinuous function. Okay. Hey, can anybody tell me the type of function you do have on the left hand or the right hand side for you? Very good. Piecewise function. It's a combination of two types of functions, right? Remember, you had the little bracket. What kind of functions do you see being combined here? What's the first one here? Linear and a. What creates this? There you go. A parabola, x squared. It's saying x from here back is going to be a linear. X from here forward is going to be a parabola. Okay. But it's not continuous. Okay. Now, there's a good way to know continuity. For one, a very base definition that we use, and we use this even in way higher maths. Hey, can I put my pencil down and do this without ever picking it up? That's continuous. Kind of makes sense, doesn't it? Over here, can I do that again though? Nope, I had to stop, pick it up. In essence, and I did in your notes, I have to change colors. Now, the thing about continuity is this. While this piecewise function as a whole is not continuous, if, once again, this happens later on in other maths, if I decided to bound this function and not look at the whole, but if I said over here at this piecewise function, if I said, hey, from negative infinity up to 0, is that a continuous function? Is it not? Look, it's going to go up to infinity. I'm never going to have to pick my line up. So I can bound that function to a section that is continuous, but the function as a whole, there's a hole in it. We call this right here a removable discontinuity. You'll learn about that later on. In this class, you'll learn about that. You don't need to know that right now. It just means somewhere where something can equal that right there. Okay? Continuity matters. Okay? So, notice left-hand function is continuous, right-hand function is not. You don't have to worry about bounding things in this class. Okay? Good? So, let's look at how you're going to deal with things when there is not a graph to look at. I'm going to leave this here for you to read. I'm just going to show you by example. How does that sound? Okay? Notice here, solve the polynomial inequality. It's just saying solve it. It does not give you a graph to look at. Does that mean you couldn't go put a graph into Desmos and take a look at it? No. I will say this. First off, I'm going to show you how to do the math. And then I'm going to show you a trick. Okay? Find your zeros first. Step 1, find your zeros. Okay? All my zeros here. If it permits me to kind of skip the math, you should be able to be pretty good at this math by now. My zeros are going to be where x is equal to 2, -5, and 4. Are we good with that? Okay. Draw yourself a number line. It does not have to be perfect. Don't sit there and think you got to like measure everything out. And graph those. Now that you need to put the numbers in the correct spot. So notice I'm going to have a -5 here. I'm also going to have a what? A 2, and I'm going to have a 4. Now, this thing is not strict, right? Not strict means I'm going to be using what? Brackets or parentheses? Parentheses, right? Everywhere. Just parentheses everywhere. That's what's nice. When it's not strict, parentheses everywhere. I'm going to create some intervals. Okay? Are you with me? I know, looking at a number line, everything going in this direction is going to negative infinity. You should be able to graph that. I know everything going in this direction is going into positive infinity. So let me look at my first interval here, and I know it's going to be from negative infinity to -5. Am I good about that? My next interval has to become between the next 0 and the next 0. So that's going to be from -5 to where? 2. And then I'm going to go from where? 2 to 4. And then where am I going?
To infinity.
Very good, 4 to infinity. Are we good? You got that okay? Could you do that pretty consistently? Then this is how hard the rest is. Watch. Come down here. Like I said, the math is going to get not messy, just it's tedious. I'm going to write down all my intervals. I got this, -5. I've got -5, comma 2. I've got 2, comma -4. And then I've got 4 to infinity. They also gave me a polynomial right here. Let me change it back to yellow. Right here. Can we all agree? This is what I'm going to do. Go to this direction here. I'm going to go x minus 2, x plus 5. And I'm only going to do this on the first one so you'll kind of see what's going to happen here. X minus 4. I know I cannot pick 5. What you're going to do is you're going to pick a test point that fits within that little interval. So you can pick anything less than -5. It doesn't matter what number you pick. Okay, in my notes, I picked -7. So you're literally going to write this like this. -7 minus 2. -7 plus 5. -7 minus 4. And hopefully you're going to put all that into your calculator and do some quick math. And then notice when I do this off the back end, I get -198. All I cared about is guess what? That's negative. You know what that means? There's a line going that direction. Watch what's going to happen. Okay? Do it again. I'm not going to do these over and over again. You can see the math behind this. In the next one, I pick 0. Okay? When I pick 0, let me just kind of come in here. When P is 0, I end up getting 40. Well, what's that guy? That's positive. Anybody have a guess what's going to happen between 2 and -4? When I pick a test point in there, which the only, I'm going to pick, why did I put -4? That's a 4, not -4. Pick 3 there, so I pick P of 3. P of 3 ends up being -8. You can pick whatever number you want. I'm just picking arbitrary numbers. Okay. And then for this last one, I believe I picked 7 again, and I end up getting 180. Well, look what happens here. I get a negative, and then I get a positive. You see the pattern? But look at what the question says. Now, this is without looking at a graph, right? It says this, where P of X is greater than what? Greater than 0. Well, when things are greater than 0, they are what?
Positive.
Positive. So the only ones I need to use are this one and this one. Because that's where the function is what? Whatever the function doing, this is where that hump starts to happen and does what? It goes up and it's in the positive area before it goes back down and dips into the negatives. and somewhere else it comes back up again. See? Okay. Because I only have 5 minutes, I'm gonna get to show you my little trick. There is a whole bunch, and we'll do some of these in the next class. But let me give you a little hint here. First off, your answer, it's not strict, right? Sorry, this is strict, so we gotta keep the parentheses. So your answer is going to be -5 to 2 union with 4 to -8. Can I ask you something though? What's the base function? X cubed, isn't it? I know that I have something here at -5, 2, and 4. Doesn't x cubed look like this? So you're telling me I could have just done this right here and said, hey, well, it's positive here to here and here to here. There you go. If you want to do it by a sketch, it works, doesn't it? How can I figure out that's x cubed? I mean, one, you could put all that in, or you could just multiply all your x's together and know you got the x cubed, right? But they gave me the zeros. So notice, just like on the last one, here, remember we did this one right here? Did I work out any math on that? No, I just found my zeros and there was a graph to look at, right? I did the same thing here. Now, does that mean you shouldn't know how to do the math? No. You need to know how to do that. You need to know how to do the math to this because sometimes you're going to need to. But that makes it pretty easy, right? Could you also Desmos it and check your answer? Yeah. Okay. And notice my drawing matches. Hey, this thing from -5 to 2 should be positive. Hey, what's happened from -5 to 2? Isn't my hump doing this? How do I know that? Because I knew my base graphs from 3.4. I know what an x to the power of 3 looks like. I know what creating zeros is also. It's where it crosses the x-axis. Is my picture perfect? Heck no. Go look at the real thing on Desmos, and it goes way up and down. I don't care. That gave me a sketch. That saved me, I mean, that right there will take you about 5-10 minutes. That took me a minute. Okay, that's for 5. You can't do that in 5.2 and 3 and 4 and 5, but still, it'll help you in 5.1. Okay. Your homework, your 5.1 has a lot of questions. Not a lot, but I did a bunch. I'll show you in here. I did a bunch of your questions on your notes. Okay, a bunch of the harder ones. I'm trying to see if there's anything in here that's weird. Before we leave today, like I said, no, these are all going to be straightforward. Look at this one right here. Find the solution. We just did that, right? Be careful with this one though. Look at the last one. That's 3 minus x. But if you still want to know on this one, if you still want to know what the degree is, you got x times what? -x. So what are you probably going to have here? X times x is x squared. Boy, don't start losing me now. Times -x. Yeah, -x cubed. Well, doesn't that just create a? You tell me you can't find the zeros for that, and then you just got to make sure. Hey, is it less than? Is it strict? Is it not strict? That's how hard that one is. Hey, you can go in there and do the math to it. I do the math for you. Okay. I think on this one, actually, I just show you the deal. This last one here. Where is it? There you go. What is the degree of this polynomial? Oh, you don't know, do you? -8x times x times -7x. Multiply those together and you're going to get what? The degree and the coefficient, the leading coefficient. And then after that, all you're going to have to do is come back down here and say, hey, if I have a negative, this is gonna be a positive x cubed, because you got negative and negative positive, so that's gonna be an x cubed. What kind of behavior does that demonstrate? Well, look at it. As x approaches negative infinity, what is happening to that? Yeah, it's going to negative infinity, isn't it? So there you go. You just put negative infinity in there. As x approaches positive infinity, what's going to happen? How much math that take? Simple calculator and a sketch, right? Don't overthink it, guys. College algebra is hard because people do too much math. It's a lot of graphs. I think if you took me in intermediate, didn't I say that? I said, man, there's a lot of graphs in college algebra. There's a lot of graphs, but the better your graphs, easier it's going to be. Okay, so. Alrighty, right on time. I will see y'all tomorrow. If you need me to work some of these, I will. But other than that, we're going to go ahead and start delving into 5.2. It's going to be polynomial long division. You did that back in intermediate. No, Dev 2, you didn't see it in intermediate.